our rice box practice using equilibrium constants to perform calculations on situations. All right. So we're going to go straight to the questions in the back here because we've gone over the notes in class except for the last one. So let's start with, okay, we've got a 1 liter vessel. All right, so we got a volume of 1 liter. And that contains some carbon monoxide. And it contains some water. I meant to make that a subscript, but forgot. And then, after 1 hour, equilibrium is reached. And this is the equilibrium reaction. Okay, so it says later equilibrium is reached. So this, to me, implies that these are initial conditions. Those are not equilibrium conditions. All right, and then analysis showed that there's a 1/4 mole of carbon dioxide present at equilibrium. And the question is, what's the equilibrium constant for this reaction? All right, so, I'm not really sure how to get started with a question like this. I don't really know exactly where to get started, but that's what rice boxes are for. It helps me direct my thoughts so that I don't have to feel confident that I know how to find the answer necessarily. If I can follow the general steps of starting with a rice box, and then we'll write a KEQ expression, and then maybe we might have to solve for something. So if we can follow those steps, I mean, that's a good rule of thumb at least. It's not going to take us to all of our answers, but hopefully it will allow us to investigate in an orderly fashion. All right, so I'm going to write out a little rice box here. All right. So my reaction is I've got carbon monoxide. I'm not going to include the phases. All the phases are the same here, and they're not especially relevant, mainly because all the phases are the same. Particularly, all of them are gases. Okay, and I know some initial conditions. I know my initial carbon monoxide concentration is 0.750 moles for every 1 liter. And because the reaction vessel is 1 liter, I can actually just write 0.750 right in here. Now that's 0.70 moles per liter. Did I say 0.70? 0.570. 750. Sorry guys, it's been a long day. And I'm trying to do 2 things at once. 0.750 moles per liter, because only concentration can go inside here, but because I have a 1 liter vessel, I'm only dividing by the number 1. All right, cool. So let's talk about, what do we got next? We have water. Okay, so it looks like we have 0.275 moles per liter of water. And it doesn't say anything about carbon dioxide and hydrogen gas. And while it doesn't say there are no moles of carbon dioxide or hydrogen, we can infer that there aren't any. All right, and then we know that at equilibrium, E for equilibrium, we know there's 0.250 moles per liter of carbon dioxide. And the question is, okay, how did things change? Well, I can see that in order to go from 0 moles of carbon dioxide for every liter to 1/4 mole, I must have added 1/4 mole. Now, I can see there's a molar ratio that is consistent between each of these terms. So, for every mole of carbon dioxide that's made, a mole of hydrogen gas has to be made. It's a 1-to-1 ratio. So that means I must have added 1/4 mole of hydrogen gas to make 1/4 mole of hydrogen gas. And if that's true, well, that means that I must have lost a mole of water, or rather 1/4 mole. because for every part of a mole of carbon dioxide I make, I have to have consumed the same number of parts of a mole of water. And the same logic is true for carbon monoxide over here. Okay, and then this is a simple subtraction. I just subtract these. This is like subtracting a quarter from 75 cents. I have 50 cents left. This is like subtracting 250 from 275. That's the way I think of it anyway, and it's about a quarter. Okay, and now we have our equilibrium concentrations. Rice box step done. Equilibrium expression next. All right, so my equilibrium expression should say, okay, well, I'm going to take concentration of my products, which is CO2, and hydrogen gas, and divided by the concentration of my cobalt, my carbon monoxide, and my water. And so that should give me and these are equilibrium concentrations, of course. So that is going to take a value of 0.250 moles per every liter, and 0.250 moles for every liter. I'm not including the units. I'm not including the units because units of equilibrium constants get kind of funky, and it's an interesting concept, but we're dealing with enough new ideas, I would say, at this time, especially with some of the kind of complicated algebra skills we're going to be reviewing when questions get a little bit heavier. So in order to relieve some of that stress, we're not going to take a look at the units argument for equilibrium constants. Okay, so what do we got here? We got a quarter times a quarter. Sometimes I like to just take these and turn them into fractions and turn them back into the right number of sig fig decimals. Just a quarter times a half times what's that? That's 2.5. It's like 25 thousandths. So it's like 5 200ths, which is like a 40th. Okay. And so it's a 1/16 over 1/80th. And so that gives us a value of 1/16, whatever this is, times 80 over 1. Because it's a division of 1 over 80, and so we flip it and turn it to multiplication. So it's 80 over 60, which actually gives us a nice, handsome KEQ value of 5. So KEQ equals 5. Now, I might just double check that and use a calculator. So 0.25 times 0.25 divided by 0.5 and divided by 0.025, 5. Okay, happy days. And so our equilibrium constant, which I'll remind you is specifically what we were asked here. We were required to give what is the KEQ for this reaction. That's the given, the required, in Graves terminology. All right, and that is our textbook rice box question. All right, so we're going to move on and see how things might get a little spicier as we move along. All right, so let's take a look at question 2. All right, so this time we've got a 5-liter reaction vessel, okay, and it had so the word initial pops up. That's going to be relevant. Initially filled with 6 moles of SO2, sulfur dioxide, and also 2.5 moles of nitrogen dioxide, and 1 mole of sulfur trioxide. After equilibrium, then we've got after equilibrium. Okay, so these are some key words here, and this question lies out those ideas very clearly. And then we've got this reaction. Okay, the vessel was found to contain 3.0 moles of sulfur trioxide. And again, the required in this case is similar to the last one. It asks, well, what is the KEQ? Okay, so if we can start by writing out a rice box, kind of similar to what we just did in the last question. Hopefully, we will understand where to go when it comes down to finding our KEQ expression. All right, so start with a rice bowl, rice box. And the reaction here is SO2 plus nitrogen dioxide, and that is in equilibrium with sulfur trioxide and nitrous monoxide. Okay, and we've got some initial concentrations we're given here. We're given an initial concentration of, so we're told that there are 6 moles of SO2, but it's actually 6 moles for every 5 liters. So that ratio, I believe, is 1.2 moles for every liter, but I'll just double check that. Yeah, it's 1.2 moles for every liter, so 1.2 molar, so that's the concentration. Then I've got an initial concentration of nitrogen dioxide, which is 2.5. Oh, but for every 5 liters, so that's going to be 0.5 moles for every liter. And I've got a mole split between 5 liters, so that if I can imagine splitting a mole into 5, that means I've got like 0.2 moles for each liter. That's of sulfur trioxide. And if I wasn't sure, I would really be just dividing 1 divided by 5. It's going to give me that 0.2 value. Okay, cool. And looks like there was no nitrogen dioxide in my initial conditions. All right. And so then we look back at the question and we say, okay, well, do we know anything else? Let's find out. Well, it looks like at equilibrium, or rather after equilibrium was reached, we had 3 moles of SO3, or sodium trioxide. 3.0. That actually sounds like quite, oh wait, right, 3.0 moles for every liter. That's why that number sounded so big. Okay. And 3 divided by 5, that's like 0.6, I think. 3 divided by 5. Yeah, 0.6 moles per liter. Okay. So again, I notice I've got a 1-to-1 ratio between all of these guys. So when I add 0.4 moles for every liter of sulfur trioxide, I must add a similar number of moles of nitrogen monoxide. And if I'm producing that much, I must be consuming the same amount on the other side, which I am. And then we've got some pretty simple subtractions: 0.4, 0.1, 0.8. And I think this is sufficient to give a KQ, or equilibrium expression. Okay, so I've got my concentration of sulfur trioxide times by my nitrogen monoxide divided by my sulfur dioxide and nitrogen dioxide terms. And those are concentrations. Square brackets means concentration. So then I'm going to just write in here, I've got 0.6 times 0.4, and that's 0.8 times 0.1. All right. And I might say, okay, well, that's 6 times 4 is 24, so this is 0.24. Keep the number of decimals that were right here, so it's 2 decimals. And multiply these guys together, so it's going to give me 0.08. All right, and so I ask, how many 800ths can fit into 2400ths? Well, it's got to be 3, right? But my intuition, I would say, is 95%, because it's been a long day, so I'm just going to double check, make sure I'm not making any dumb mistake here. And we get 3. Yeah, it is. So our KEQ for this expression is 3. Okay. So let's move on to question 3. Okay, so we've got the Haber process going on here. We're making ammonia, consuming nitrogen gas from the atmosphere and hydrogen. And at a certain temperature, you can put 3 moles of nitrogen and 2 moles of hydrogen into, again, a 5-liter container. And then we mentioned at equilibrium, the following is true. So that means that these guys must have been initial conditions, right? And then these are equilibrium conditions. then we've got a concentration of ammonia is 0.020 moles for every liter. That's interesting. So we're given information in moles and in molar. And we're asked to calculate the equilibrium concentration. Okay. All right, so to do this, we should probably start with a rice table again. Rice box. All right, so just make a bit of room here. There we go. Let me zoom in a little bit here. Yes, all right. Rice. My reaction is the Haber process, 3H2 plus, 3 N2s, pardon me, H2. That's at equilibrium with 2 ammonia molecules. I can't write and talk at the same time, apparently. All right. Don't need these necessarily, but something tells me it will help me keep things straight. Okay, so what do I got here? I have 3 moles of nitrogen in 5 liters. Okay, so I think that's 0.6 molar, right? 3 over 5, 0.6 moles per liter, or molar. So that's that was nitrogen, so 0.6. And then I've got 2 moles of hydrogen split between 5 liters, which I think if I divide 2 into 5 pieces, I get 0.4 pieces each. 2/5 is 0.4. And do I know anything about ammonia? I got ammonia here, but then it looks like that's at equilibrium. Okay, maybe I'll throw that in though. And ammonia I know is 0.02 at equilibrium. That's this guy here. So at equilibrium, 0.020 moles. All right, and we can assume that there was no ammonia to begin with. And that makes our work pretty easy here. We can see that we're probably going to be adding 0.020 moles, which means we must be consuming, wait a second, this isn't balanced. Oh gosh. Well, if you didn't notice, this was not a balanced reaction. Oh no, we use the same reaction twice. Okay, that's fine. It really should be a nitrogen. I'm going to cross it out. Nitrogen plus 3 hydrogen. And that's related to 2 ammonias. And now that's a nice balanced reaction. Alright, I'll have to remember to edit that. I'll try and point that out in class tomorrow and also on Google Classroom. Okay, so now, in that case, let's check out these molar ratios here. Oh, the molar ratios are not super friendly, but let's see what we can do. Oh, okay, good. So I can see that my molar ratio of nitrogen gas to ammonia is about 1 to 2. So if 2 moles of ammonia are produced, that means 1 mole of nitrogen gas was consumed. And so what that means is that I'm going to find I'm going to be consuming exactly half this number of moles for every 1 liter. So half of 200ths is 100th. 100th is what I'm trying to say. And we'll also be consuming 3 times that many hydrogen moles. So I'm also going to be consuming 3 times as many hydrogen moles. And you can check with the calculator to confirm that this is 3 times 100th. And okay, now we can do some arithmetic here and say, okay, I think that gives me 0.59 moles of nitrogen and 0.37 moles for every liter of hydrogen gas. Okay, and then we can move on to our KQ reaction equation. So that's going to say we're going to give our concentration of products is ammonia squared over nitrogen times the hydrogen term cubed, concentration cubed. And that's at equilibrium, of course. So then we're going to take our equilibrium concentrations and plug them in. That's squared. Nitrogen is at 0.59 and hydrogen 0.37 cubed. And I don't think this is the sort of calculation I can do successfully in my head. I think I would not have success at that, so I'm going to pull up the calculator. Divided by 0.59 equals, divided by 0.37 cubed equals 0.0134. 0.0134. How many sig figs did I have? Well, it looks like I only had 2, so I'm just going to call it 0.13. All right. Oops. I realized I was just off the page a little bit there. Okay. So let's move on. I'm going to just move that camera a little bit. Okay. So for question 4, we're also going to imagine this was properly balanced and not erroneously written. Okay, so we got this same reaction as the Haber process. And now we have a different temperature where 6 moles of ammonia are introduced to a 10, okay, so let's highlight here. 6 moles of ammonia, 10-liter container. And at equilibrium, there are 2 moles of ammonia left. Okay. Calculate the equilibrium constant for this reaction. All right. This is going to be similar. All right. So for question 4, again, we're going to start with a rice table, rice box. And we've got a nitrogen and 3 hydrogen gases living in equilibrium to ammonia gas molecules. All right, so my initial concentration of, what do I have here? Some ammonia introduced, 6 moles of ammonia in a 10-liter container. So that sounds like I've got 0.6 moles for every liter. Okay, but at equilibrium there was only 2 moles for every 10 liters, so that's 0.2 moles for every 1 liter left. All right, and can we reason what the equilibrium constant is here? Okay, so looks like we're going to remove 0.4 moles of ammonia. And if 0.4 moles of ammonia are removed, well, that means half as many moles of nitrogen were produced. So that means we're going to make half as many moles, but we're making 3 times as many hydrogens. So 3 times as many as this, that's 0.6. And it looks like we started with zeros. And so then we get an equilibrium 0.2, 0.6. I'm going to take my equilibrium constant from the expression from the last question and just rewrite it out. Well, I'm not going to even rewrite it out, I'm just going to use it. So it says my equilibrium constant is the square of ammonia concentration at equilibrium divided by the nitrogen and the cube of the hydrogen concentrations. Okay. Ammonia is 0.2 squared over 0.2 times 0.6 cubed. Okay. This is something I think I could probably do comfortably without much help from a calculator. So this is 0.2 squared, which is 0.2 times 0.2. Means I can cross out these terms. And then I've got 0.2, or a fifth, on the top. And I've got 3/5 to the power of 3, which is a fifth over 27 125ths, right? That's cubing each of those. And it says the same thing as 1/5 times 125 over 27. And I can simplify it diagonally and leave with 25 here by dividing by 5. So that means my answer is 25/27. Now, of course, 25/27 gives the incorrect level of precision. It implies we know this to an infinite degree. So I'm going to write this to, how many sig figs? 2 sig figs. So my k cubed equals 0.93. And that's worth checking with a calculator. 0.2 squared divided by 0.2 equals 0.2 divided by 0.6 to the power of 3. There we go. Okay, I was on the right track. All right. Okay. So question 5 asks us to compare our answers in question 3 and question 4. The Haber process, which is the reaction in these two questions, is exothermic. And the question is, well, does that mean the temperature in question 3 is higher or lower than the temperature in question 4? Okay. Well, let's just take a look here. In question 3, we had our equilibrium constant of 0.013. In question 4, our equilibrium constant was 0.93. Okay. So this question is a little nonlinear. It's going to require a bit of 3C thinking here. All right, so arguing the Haber process is exothermic. So let's write that out as if it is. So I'm going to write a little diagram here. That says to me that my nitrogen and my hydrogens live up here. And they're going to go down a slide as the reaction progresses, losing their bond energy and releasing it to the universe in terms of heat. So we're going to lose enthalpy. And then we get 2 ammonia as a result. Okay. And that just is a visualization of the idea that it's exothermic. Okay. So what does that mean? That means that, okay, so if it's exothermic, okay. So we know that let's take a look at an exothermic reaction. If an exothermic reaction is increased in temperature, how does this affect the equilibrium constant? Okay, so we've got some reactants that lead to products, or maybe live in equilibrium, products plus enthalpy, right? Okay. So an exothermic reaction means it's exothermic in this direction. And this is endothermic. And we know that equilibrium constant is a ratio of the products over the reactants. Okay. So if we increase the temperature, well, what happens? Le Chatelier's principle says this wants to undo that increase, which means shift equilibrium to the reactants as a result. And that means it's going to decrease the concentration of the products, right? Because some of these products are going to combine with some energy and turn them back into reactants, removing some of the energy from the system, trying to undo this increase in temperature. So products are going to decrease and the reactants are going to increase. And the result of a fraction where you shrink its numerator and grow its denominator is that means that KEQ is going to reduce. Okay. So an increase in temperature must lead to a decrease in KEQ. Okay, and now we can look back at our KEQs. We can say, okay, since, let's label this KEQ3 and KEQ4. KEQ3 is smaller than KEQ4. The reaction must have occurred at a, hang on, let me just think this through. I want to make sure. I think it's important to think deeply about these things and double check ourselves, our intuition. Okay, increase in temperature means we decrease in equilibrium constant. Okay, so if you decrease in equilibrium constant, that means you had an increase in temperature. So that means this reaction with the smaller KEQ must have occurred at a higher temperature. Than KEQ4, than reaction 4. And that is a pretty challenging question, I think. All right. Okay, we're on the home stretch. I think we have a couple more equilibrium constant expression rice box questions to work through. So let's move on. All right, question 6. So we've got a equilibrium constant of 5. That's at some temperature. For the reaction, this reaction, okay, great. And so we have some amount of sulfur trioxide placed in a 2-liter reaction vessel. That's going to be important. And at equilibrium, the vessel contained 0.300 moles of oxygen. And the question is, what concentration of sulfur trioxide was originally placed in the vessel? Okay. That sounds a little tricky, so let's see what we can do. We're going to start with the rice box, then we'll go to a KEQ, and then we'll see if we can penetrate this question any deeper than we already are. All right, so right now, we don't know very much. But we know reaction. So I'm going to write that in. 2SO2 plus oxygen. Again, they're all gases, so I'm going to just leave out their phase for now. And what do I know? I don't know anything about my initial situation, except I know there was some initial sulfur trioxide. And we can assume no oxygen. And at equilibrium, there's 0.30 moles. Oh, oops, for every 2 liters. So actually that's 0.15, half of 0.30 moles of oxygen. Oxygen, ozone, oxygen. Yikes. Man, this practice sheet was full of typos. I do apologize. Okay, so what's the concentration of sulfur trioxide originally? Okay, so we know some of this sulfur trioxide was added, but we don't know how much. I'm going to choose letter X to represent that unknown value. Furthermore, I know I must have increased by 0.15 moles for every liter of oxygen, which means I must have increased by twice as much. So, sulfur dioxide, because the ratio is 2 to 1. For every 1 oxygen, 2 sulfur dioxides are, in this case, produced. And an equal number of sulfur trioxides would have to be consumed. So I get this value x, take away 0.30 and 0.30 here. All right. That's fine, and now I'll go to my KEQ expression, which says that concentration of my sulfur trioxide, which is 0.30, squared, over the square of sulfur dioxide times the concentration of oxygen. It's going to give me, oh wait, I know it's all equal to 5. Okay, I think this is a pretty solvable question. So what I'm going to do is I'm going to multiply the bottoms together. It's 0.3 times 0.3, which is 0.09, times 0.15, I don't know, 0.12 or something, I don't know, 0.3 squared times 0.15 equals 0.0135. Okay, so we get x minus 0.3 squared over 0.0135, and that's all equal to 5. So the next thing I want to do is I want to multiply both sides by 0.0135. And I can put brackets around that to indicate what I'm doing. These guys cancel out. I get x minus 0.3. And we're going to multiply that value by 5. We get 0.6, pardon me, 0.0675. Now, if you see this enough in math class, you may feel an impulse to expand this binomial. I encourage you not to. It is going to be messy, and then we will need a quadratic formula to solve. In this stage, we can actually just undo a square by square rooting on both sides. Now, if we were in pre-calc 12, we would be concerned about adding a positive and a negative version of the square root to both sides. But we're not. We're in chemistry 12. We can kind of ignore the negative term in this case. And then we need the square root of this thing. What's the square root of this thing? 0.260. And then lastly, to isolate x, we're going to add 0.3 to both sides. And so that means our initial, oh wait, sorry, I'm going to just do this calculation first. That's 0.560. Okay, now, we are not done until we remember what did x represent. We should translate this into language. Well, x represented our initial sulfur trioxide concentration. So this means our initial SO3 concentration was 0.560 moles. And it just so happens that in this case, the variable we were looking for happens to have been the value the question asked for. And they did not have to be true. We might have had to have done some more thinking here. In this case, I think we're done. Okay. All right, let's do this last question. So question 7, we've got an equilibrium constant of 35, and we've got some reaction, and we know that at equilibrium, that's an important phrase, we have a concentration of phosphorus pentachloride that is this much, and a concentration of phosphorus trichloride this much. The question is, what is the equilibrium? What is equilibrium constant concentration? Pardon me, the equilibrium concentration chlorine gas. So I think you guys are starting to get the hang of setting up rice tables, so I'm just going to speed into this one a little bit. All right, the reaction, PCl, 5, PCl3 plus our gas. And we don't know anything about the initial concentrations, but we're asked for the equilibrium concentration of chlorine. We know the equilibrium concentrations of phosphorus pentachloride is 1.34 times 10 to the negative 5. And I know this guy is 0.205 molar. And what is the equilibrium concentration of chlorine? How are we going to start this question? Seems hard. Alright, because what I notice is that there's no information specifically connecting all these values. Interesting. What am I overlooking here? Oh, I see what I'm overlooking here. Apologize for that, guys. Okay, so this is not what we were asked. We were asked for the equilibrium concentration of chlorine gas. Well, to answer that, we actually don't need a Rice table. We're not asked about the initial conditions. All we need to do is say, well, the equilibrium constant is 35.0, and that's equal to the concentration of our PCl3 times our chlorine gas divided by our concentration of Cl5. And so we'll just turn that into a nice equation. I'm not going to write 35.0, just write 35. 0.205 molar times X, that's our unknown, divided by 1.34 times 10 to the negative 5. Okay, so I'll multiply by my denominator to cancel it out, but I got to do that on both sides. Times 35, so it's 1.34 to the power of negative 5 times 35. And I get 4.69 times 10 to the negative 4 is equal to 0.205 times x. I'll divide by 0.205 to cancel it out. I get x is whatever this is divided by 0.205. 2.29 times 10 to the negative 3. And that's it for our KEQ practice questions. For now, I actually think you could use some practice with some of the harder questions as well, but I thought this would be sufficient to get the ball rolling on these rice boxes. And when we do a little bit of extra practice and we look at a question on Monday, then we'll come back and we'll do a few more challenging ones before the unit test on Thursday. Let me know if you have any questions with any of these practice questions.